Hello, Pamela.
Hello.
Hold on, let's get you out, coming out of the headphones. Talk now?
Hello.
Perfect. You are in my mind.
That's a good place to be. I can join all the other voices in your head.
I can join all the other voices in my head. Hey, it's Astronomy Cast with Fraser, Cain, and Pamela Gay. So we're going to hit you up with a last-minute show change. So I know you think you're going to come for the Becquerel experiment where they discovered radioactivity, but it turns out that's not what we're doing. We're going to do the Millikan Oil Drop experiment. So if you're severely disappointed and you're a huge
Just come back next week.
Becquerel fan, then come back next week and we'll cover it then. If you're a Millikan hater, then again, you won't have to listen to his filthy, filthy experiment this week, and come back next week. But if you really you're here for the science and you really don't care whether it's this experiment or that experiment, then stay tuned and we will perform for you a live episode of Astronomy Cast. So, as always, you can join the show. Hit us with your questions. Of course, you are going to have to throw out all your prepared Becquerel experiments on radioactivity and prepare a fresh set of electron charge questions. We'll be patient and
You're going to give
understanding.
me so much grief for changing topics, aren't you?
I really am. Is that not clear to everybody that that's what I'm doing? Is I am really giving Pamela a hard time here for changing topics at the last minute.
I didn't. I did exactly what was in the calendar. I looked at the calendar. I prepared what was in the calendar.
Clearly, there's some kind of breakdown in the calendar or the
I think
system.
multiple calendars is the problem.
Yeah. There's a lot of calendars, so we need to find the true calendar that really defines the future topics. Anyway, it's not like this happens all the time. This has happened like
One
once.
other time.
Yeah, one other time, so it's fine. This month. Okay, so anyway, ever? Yeah.
Yeah.
Right. So go ahead and join the conversation. Just click on the Q&A app. If you're watching the video, you can post some questions in there, and we'd be glad to incorporate them into the show. I'm going to say hello to Douglas Crandall and Noel Rippenthal and Albert Braun and Sev Dustbunny and Tom Van Scotter and Nancy Graziano and Oleg Stroganov and Halcyon and Michael Jobin and Ed Thompson and Rick Schwartz and Giselle Savarine and Peter Waldman, Guido Bibra and Helga Bjorkog. That's awesome. What a crowd.
Yeah. That's cool.
Yeah. And so so we'll stick around after the show and we'll answer your questions about space and or astronomy and or physics and or chemistry, I guess.
No, please don't do that to me.
Well, in that using chemistry for really clever physics experiments is acceptable.
There's no chemistry harmed in this experiment. It was pure physics.
I don't know. Oil with other oil, knowing that oil has physical properties.
Yeah, the oil had nothing to do with it.
All right. You just won't let anything go, will you? You're like a pit bull.
I'm simply drawing a line and saying I do not know organic chemistry.
Chemistry is irrelevant.
No, chemistry is just not going to be answered.
We're just going to tweet this. Pamela hates chemists. All right.
No, I'm fine with chemists. I'm fine with other people doing chemistry. I just know my limitations. If it has molecular bonds, I'm probably not the person to talk to.
I understand. It's all physics anyway. Okay, so so we'll take about 20 minutes, 25 minutes to record the show, and then we'll answer your questions about space and astronomy. So, how are you in the recorditron?
I'm ready to press record. Shall I press record?
I'm going to say yes.
I'm pressing it. My computer is recording. Hey, you are Fraser. Hey, Preston.
Hello, Preston. Enjoy this Astronomy Cast that we are about to create for you. Oh, okay. Here we go. Astronomy Cast, episode 372, the Millikan Oil Drop Experiment. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
I am doing awesome. Yeah, I can't complain. I can't complain about the terrible, horrible, rainy weather that's just never seems to end.
You
But
live.
but at least as a Canadian, I know I'm one of the lucky ones.
I was
So
going to say you're kind of on the west coast
yeah,
in tropical, what is it, mid-latitude
yeah,
tropics?
yeah,
Yeah,
exactly.
okay.
It's Pineapple Express all the way here. Um, so let's just remind people that there's going to be a live event where we get to watch Pamela try to help raise money for research.
Yes. So on April 25, 26, we are going to be holding this year's CosmoQuest Hangout-a-thon. You can find out everything you want to know by going to cosmoquest.org/hangout-a-thon, all one word. Um, and we're still in the process of pulling things together, but what I can tell you right now is we are partnered with Astronomers Without Borders, and we'll be bringing you star parties around the world as the night passes from nation to nation. We're also going to have scientists coming on to help us understand the entire process of asteroid and meteorite understanding, folks talking about the moon, Mars, and we're going to be actually racing to map out other worlds with data visualizations to see you as you compete to get Vesta, Mercury, the Moon, and we'll have Mars for the Hangout-a-thon all mapped out in real time. And so it's all about science and hopefully funding science. The only reason I am here is because folks like you have donated. CosmoQuest needs your help. So yeah, cosmoquest.org/donate if you want to get in ahead of the game.
And
Thank
that
you.
date again?
It is April 25, 26. We're running from 8 a.m. Pacific to 8 p.m. on Sunday Pacific time, 36 straight hours.
Sweet. All right. All right, let's get cranking. So, in 1909, Robert Millikan devised an ingenious experiment to figure out the charge of a single electron using a drop of oil. So, let's talk about this Nobel Prize winning experiment. This is one of my favorite experiments, and I remember being in physics class in high school. Like we were grade 11, I think, and they explained the oil drop experiment, and it blew my mind in its simplicity and sort of out of the box thinking to figure out a way to come up with a fundamental calculation of the universe, and is still just an amazing experiment. So set the stage. What was the unknown at the time?
Well, at that point, we understood that there were positive and negative charges out there. What we didn't know is if they were associated with quantized individual particles that came with set charge, or if this was a continuum, or what, basically. We just didn't know. And so what Millikan and Fletcher, who never gets mentioned but was his PhD student at the time and who did the experiment and designed the apparatus, and then was left off of the paper, what we know is the work that Fletcher did actually allowed them to find a way to look to see if charge only appeared in certain multiples that would allow us to say, well, every time we see charge, it's a multiple of this unit, which means there is a fundamental amount of charge that you don't get smaller than.
And so the possibility it was figured out was that it was I guess the difference between it being binary and it just was like a field that increased or decreased in strength, that you could have the charge be 0.001, 0.002, or anywhere in between. There was no distinct jumps that the charges went through, and so they were trying to figure out whether it was just this distinct charge or whether it was I'm looking for a word and it's not coming to me, but
they were trying to figure out if it was a continuum or if it was quantized. So this is basically the difference between at the macroscopic scale, the amount of applesauce that you have in your bowl is a continuous number. You can have a little bit more, a lot more. Applesauce doesn't come in quanta, but apples do. You can either have an apple, you can have two apples. An apple is a quanta of apple that you are limited on what you can put in your bowl.
digital or analog? Is it
Yeah.
digital or analog? So you imagine some old school stereo where you sit in front of your stereo and you're cranking the volume and you're just like turning it up and turning it down, and it's analog, right? And as opposed to when you take your iPhone and you turn up the volume and it goes in discrete volume levels,
That are never
that's
good volume
they're never
levels.
good levels, no, and it complains and won't let you go past a certain volume, even though you try to like change the settings. It never holds the settings, and every time you turn your phone back on again, it forgets the settings. And anyway,
Are you a bit annoyed with your iPhone, Fraser?
yeah, a little. So, but that's the question. So the question is it? And so quantum theory, which was just being developed at this time, was coming up with sort of a whole series of theories about what this meant, about what quantized energy states meant.
And so to paint a picture of where we were, this was all happening in the 1900s. The paper came out in 1913. The research started around 1908. And this was a point in time where we were starting, not we, I wasn't born, my grandparents weren't born. The field of science was working on trying to understand how to play with all of their new electromechanic toys. We've known about electricity for a while. Benjamin Franklin is the person that we all think about, and is actually one of the first people to start figuring out things like using capacitors to store charge. One of the things that I learned in preparing for this particular Astronomy Cast was that batteries were figured out in the late 1700s because in 1780 Luigi Galvani was dissecting a frog, and when he touched his iron scalpel to the brass hook the frog was attached to, the frog's leg jumped, and he assumed that the dead frog had some sort of intrinsic energy still in it, which is a really horrifying thing to imagine. But what was actually discovered, as explained by Alessandro Volta, was if you have a voltaic substance, or electrolytic substance, in this case, the guts of the frog.
The guts of the frog, yeah, and the fluids.
You combine a couple of different metals, the brass and the iron, this generates charge. So fast forward 200 years. And they have this ability now to build batteries, often by taking briny water and soaking cardboard in it. Briny just is a fancy word for salty. You use it to make pickles. Take cardboard, soak it in brine, and then layer various metals with this briny cardboard, and this will actually output electricity. And they knew how to wire this up. They knew how to create electric and magnetic fields. And so Millikan and Fletcher realized if you have something that's charged and you have an electric field between two plates, so you take one plate of metal, you take another plate of metal, separate them with an insulator to keep them at a known separation, wire them up to a battery, they will collect charge on their two surfaces to create a constant electric field between the two surfaces. If you put something that's charged between those two surfaces, you can delightfully make it float. This is actually something that if you are daring and experimental, you can play with using just simple things you have around your house. If you have a powerful enough battery and little plastic balls, you can actually like grab a cat and use some non-conducting thing to rub the plastic balls in the cat. Charge will build up on the plastic ball because of, this is my favorite word in science, the triboelectric difference in value between the cat and the plastic ball. You now have a charged plastic ball. Stick it between two metal plates that you have safely attached to a battery. And if you get the charge to weight ratio just right, you can hover that little ball using the electric field.
My favorite, although it's not exactly the same, but it's just a great experiment, is take a comb, brush your hair, and then hold the comb right next to a stream of water that's coming out of the tap, and it will divert the stream, and then as the static electricity runs out of your comb, then you can start again, run it through your hair. Not that I can anymore, but one could.
You can do this to a cat as well. Cats are a great source of electrostatic
exactly.
charge.
Right. But it's a great thing to do with your kids is to give them a comb, have them generate static charge, and then see what things are which are pushed or pulled by the static charge. But anyway, we let's get back to the show.
Okay. So your happy little charged ball is actually not that different from the oil drops that Millikan was using. Anything that can hold a charge can be used in this experiment. So the reason he used oil drops is they didn't exactly have the greatest of batteries back in 1908. So when you had an electric field, you needed little tiny things to put charge on to try and make cover, and oil drops were a perfectly reasonable thing. The other reason was they needed things small enough that they'd hit their terminal velocity, that they'd accelerate through the air until they reached a point where the force of gravity trying to accelerate them downwards versus the buoyant force of air acting as a friction sort of kind of analog force, basically the buoyant force pushing up, balanced so that the object is no longer accelerating. So in order to get something tiny enough to suspend in the electric field and that would hit terminal velocity quickly enough that it would hit terminal velocity within the experimental apparatus, Fletcher and Millikan opted to use oil drops. They used a small sprayer, not too different from what you'd use with perfume, to create little tiny droplets. And just the action of shooting through the nozzle is enough to transfer some charge onto the oil drops. They sprayed this above a set of electric plates that had a hole in them to allow some of the oil drops to just happen to fall through the hole. And while looking between the electric plates through a magnifying apparatus, they were able to adjust the strength of the electric field to, select out oil drops that had just the right amount of charge and amount of mass to be able to be suspended within this field.
Right. So I can just imagine they've got this oil sprayer, they've got these two charged plates, in between there's a gap, they've got a knob, and as the oil drops are sort of dropping through into the charged place, they're falling really quickly, and then they turn the knob up to increase the charge, and the speed starts to slow down as the upward force of the charge on the particles, on the charge of the oil drops, is countering the gravity that's pulling them downward, and you hit this equilibrium where the particles just sort of stop hovering in between being pulled upward and being pulled downward by the gravity. And then fancy math?
Sort of. So the math wasn't actually all that fancy. It was just kind of annoying because you had to get all the variables to cancel out. So the problem that Millikan and Fletcher and Millikan were left with was you have these little tiny oil drops, and you can't really accurately hold a ruler up to an oil drop and go, okay, what's your radius? But they did know the density of oil really accurately, so they could get at the mass of the oil drops if only they could get at the radius accurately. So to get accurately at the radius, what they did was they figured out, what is the terminal velocity of these little tiny oil drops? And the terminal velocity was related to a whole bunch of different parameters that they could calculate. And once they got at the terminal velocity, they could also get at the weight of it by taking, they knew the density, they could get at the radius via the terminal velocity. So if you know the density and you know the radius, you can then calculate the weight by going, here's the radius, I know 4/3 pi r cubed is the volume of the sphere, multiply the density by that. That gets you at its mass, multiply that by the acceleration of gravity. You now have the downward force of gravity. Lots of math that's not difficult, it's just monotonous. Shoot for the monotonous math. And what you're left with is an understanding of the radius, the downward gravitational force, the upward buoyant force, And then you're in a position where you can calculate, well, what's the electric force? Now, the electric force is a function strictly of how much charge is on the object. So if you measure this whole rigmarole, go through all of the same crazy math over and over for multiple oil drops, you can start to see, well, this one has this much charge on it. I can tell because of the electric force it must have. And this one over here has this much electric force on it. You can start to realize, okay, are all of these numbers multiples of each other? And ask, does that mean that the charge is always a multiple of some core value?
Right. So you might notice that say this one's got 5, that one's got 10, this one's got 35, that one's got 100, and you might say, maybe these are a multiple of 5.
Exactly. So unfortunately the math wasn't that clean. And what gets me is they were able to go through all of their maths, and they came up with a value of a single electron having 1.592 times 10 to the minus 19th coulombs. Their published value was within about 0.5% of the actual value of the charge on an electron. So this was actually some really impressive work that they did, but it wasn't without controversy.
What?
So,
right, it took a little while before the Nobel Prize was awarded.
Well, that wasn't so much the problem. The problem came much later when people started looking at the results a little more closely. So the first thing to come up was, wait, you seem to have thrown out a lot of outliers, dear Millikan. And the truth was that Millikan did throw out a lot of data saying, well, these things simply weren't fully analyzed, that related to charged particles that may not have had as close to the center of values as some of the other experiments. So had he included all of the data he took in his initial publication, his error would have been higher, and he still would have been within 2% of the actual value. He still would have had about 2% error in his results. But he didn't want to leave that much wiggle room for detractors, so he only published the best, or at least only published the stuff that told the story he was hoping to tell.
So he cherry-picked the evidence.
He did. Now, the other thing that was pointed out by Feynman was not only did he cherry-pick the data, but then there was this problem over the following years that as people recreated his experiment, did experiments that yielded different ways of getting at the charge of the electron, people kept coming up with higher values. But no one was willing to step forward and say, hey, my value is like 2% higher than his value, or 0.5% higher, as the case may have been.
Right, because Millikan is a god, and how dare we... Right.
So everyone was like, we're getting a different number. What's wrong with what I did? And so there was never this question of what was wrong with what he did. There was a whole lot of self-doubt among all of these powerful physicists all over the world working to recreate an experiment. And I find it fascinating that instead of using the scientific theory as you're supposed to test your hypothesis, to verify results, all of these people did the scientific process up until they got results that weren't identical to what some other famous, powerful, Nobel Prize carrying dude got. And then they suddenly became very worried and looked for ways to get their value closer to his value. And it actually took several tens of years to get at our current value of the electron.
Right, but people had come up with other methods of calculating the charge of an electron, as you said, not just this one ingenious experiment with cherry-picked data, but other methodologies, right?
But even with these other methodologies, they were very cautious about saying, no, the electron's value is actually significantly higher. So if you look at the published value of the charge of an electron, It just ever so slowly crept up until it started basically hovering at the value that we now very precisely know.
But I think the implication of Millikan's data and Millikan's experiment was to provide evidence to this idea of the quantized state of the electron, and that created a very fruitful level of research after that.
It did, and the sadness that I have is even as we do this, we're referring to this as Millikans Work, and
Fletcher.
Yes, and Fletcher. Let's keep saying Fletcher. Let's rewrite history a little bit to be more accurate. Now that Fletcher's dead, people have had access to his letters and seen the documents where Millikan basically said, look, dude, if I leave you off of the paper, I'll make sure you get a cherry job at Bell. It was phrased a little bit different, but that was the gist of what was said. So this all told was one of those projects where Millikan knew he was doing something amazing. He knew, well, actually, that Fletcher was doing something pretty amazing, that this had a lot of potential to change how we, not change, but to focus how we do everything. Let's stop looking for the continuum idea of charge on the electron and start admitting electrons are discrete particles that have discrete amounts of charge. And that suddenly focused science greatly, and yeah, that was a good thing. It's just sad that it came in such a let's leave the grad student off the paper kind of format.
That seems to be a theme in your research into these historical topics.
It's not something I purposely look for.
Maybe it just happens all the time.
That's my concern, and I know I've gone out of my way to consistently not do that, and the thing is, when you choose not to do that, there's always the, well, you don't publish enough, you don't do single author papers enough, old guard complaint. So we need to change the entire field so that the people doing the work, which are often the graduate students in the lab, get the credit for their amazing contributions that allow our field to progress, while as senior and mid-career people, I'm a mid-career person, well as we're stuck writing grants 90% of the time while they're in the lab, and let's acknowledge that.
Right, but I think you've made a case. I mean, we don't want to destroy this episode of Astronomy Cast and go into this, but I think you've made a case both ways, right? That it is the senior researcher who's putting their name and saying, I stand for this research, all this research that's getting done. And they helped raise the money, and they convinced the powers that be that this experiment should be done and that the money should be spent and that the results are high quality. They are the leader of the research team that gets this work done. And if various team members drop out, at the end of the day, it's still that researcher's name on the paper. And there's value to that. And of course, you want to have the names of all the people who were involved on the process. And I guess different research teams will, depending on who they are and how magnanimous they are, will have their name first and then everybody else's name as well. And others will just only put their name on it. And I think that's, just like credits, you can make sure that everyone's role is done. But I think as the Nobel Prizes are awarded, I think there is something to be said for the person taking a stand for the research, for organizing it to be done, to make sure the money is set aside, that people can work uninterrupted, and the discovery can be made. So it's tough to decide which way
there's a difference between who's on the Nobel and who's on the paper. It's getting left off the paper where you have infinite space. Well, not infinite, you have page charges, but it's a tricky issue, and to see it come up over and over throughout history is kind of heartbreaking. You have to wonder how many careers got lost simply because the person doing the work in the lab was just a student, even though they were the ones who were devising the apparatus, saying, hey, I have this idea, let's try it. It's an interesting thing to think about and to consider as we try and define how to move forward.
It sounds like a book, Pamela.
Yeah, after I write these grants, I have to pay my bills first.
Yeah, and then write a book.
Donate, cosmoquest.org/donate. Free me from grant writing to actually do content creation in science.
That sounds great. Um, cool. Well, thanks, Pamela. Thanks, Millikan and Fletcher. And we will see you next week.
Sounds good.
Save that bad boy. Yeah, I'm telling you, I'm hearing a book here.
Wasn't intended. It's just something I keep finding and keep getting
Well,
annoyed
I
by.
think it's a great idea for a book. All I'm saying. I mean, I'm wrong.
You're not wrong. I just don't
I'm
have
not
time to
saying you
write a
have to
book
do
right
it. You know,
now.
it's handed out. Um,
Someone out there, do you want to write a book?
Write a book about and then put Pamela's name on it, obviously, because that would be the horrible irony. But essentially about the number 2 people in science whose names
Yeah.
are left off the papers. I love it. And other people watching this are nodding right now, and they're going, yeah, that sounds great. And Pamela's just the person to write it. Okay, let's just upload this thing, and then let's move on to your questions about people left off papers.
Greetings, everyone, from the great state of confusion. I want to know where you're located, Ed Thompson, and if it's Illinois, I shall smile and agree.
Okay, here we go. Yeah, Ed Thompson says, greetings from the great state of confusion. Hello, Ed. Oleg says, what is the most realistic proposal for an interstellar mission?
I'd have to go with the plans to find an asteroid, hollow it out, and set off in a generation ship.
Well, let's not even talk about people. Like, let's just talk about, like, even just robots.
It's called Voyager.
Okay, so let's go faster than Voyager at 70,000 years.
I don't think we currently have anyone really working on that plan.
Yeah. I mean, I think that the problem here is, one, I highly recommend you go to a website called Centauri Dreams, which is run by Paul Glister, and he posts a ton of great stories about this. And we actually had him on the Weekly Space Hangout a couple of weeks back. One of my favorite people thinking on this. He's on the Tau SETI Foundation and has written a book about a feasible interstellar probe. So Paul Glister. And the problem is that the faster you go, the more you're slamming into the interstellar medium. And theoretically, I think people did calculations that if you're going like a significant portion of the speed of light, you are star hot by the amount of material that you're ramming into. So, and the radiation levels would just be incalculable to the people if you tried to have people be actually on the spacecraft. So you have to go slower. And if you go slower, like 10% of the speed of light, 5% of the speed of light, 1% of the speed of light, the most realistic way to get that kind of speed is with light sails. And so you can take a spacecraft, take it really close to the sun, get a huge boost, and then have huge lasers that zap the light sail as it goes past and accelerate it. And so you could theoretically have way stations from here all the way out to the Oort cloud, and as the solar sail goes past them, these big super lasers just keep zapping it and speeding it up, and then you try to get to the star at the destination, and you aim right for the star and brake by the photons, and hopefully you stop in time, or you do braking maneuver, right? So you do almost like you do atmospheric braking, but you're doing it with a solar sail, just doing pass after pass, so you get pulled into orbit around the star. So, but the speed is the problem. Is the faster you go, the more destructive it is.
And the issue also becomes one of energy generation. We don't have sufficient energy for that kind of laser here on Earth. How are we going to stick them on other worlds?
Yeah, out in space. Yeah, no, it would require unfathomable amounts of energy.
It's technology we don't currently have. Now, if you just want to send a robot, ion drives, we've got that one figured out, folks.
Yeah, no, but even so, to take an ion drive that you're going to be able to accelerate to interstellar speeds is again too much. So it's how can you, and if you're going to scoop your particles from space, you need an enormous scoop, and the the structural materials to do that doesn't really exist, and the speed of the energy on the reactor, even if you run like an antimatter. I just read a great article just recently that an antimatter drive probably won't work because they'll run too hot, and there's no material can handle the heat that would happen from an antimatter drive running full bore to get you from star to star. So
You're just
so
going
it's
fast.
you're all just you're going too fast, and so the problem is, and
Well, no, you're even thinking with the ion drives. I mean, unfortunately, really the only way we can currently look at interstellar travel is to imagine this is something that we launch a ion drive, little tiny spacecraft that has all of its energy going into communications. Well, not all. You have to have a couple cameras, or it's not worth sending. But almost all of its energy goes into the communications, and that little ion drive that gets going at New Horizons speeds, that's really what we'd need to use is New Horizons speeds
and it's
with
not
something
even
tiny.
and
It's
even New
generations.
Horizons.
It's
Yeah, it's generations. So you've got to be cool with in the book I was talking about that Paul Glister does. He looks at 100 years. He says, we could probably feasibly send a teeny tiny probe to Alpha Centauri in 100 years using technology that will probably develop in the next 100 years. That's possible. But the great thing, if you're more patient, make it 1,000 years. Then the technology gets easier. Be even more patient. Take 10,000 years. We've got those. That's New Horizon speeds, right? Almost. So that's all. It's we all want to just be zipping from star to star in our spacecraft, and being Captain Kirk, and that's just
not so
just
feasible.
not going to happen unless Sonny White's warp drive works. So. Graham Sticking says, Lord Kelvin said, in science there is only physics. All the rest is stamp collecting.
That is pretty much true. Although, unfortunately, the mathematicians then come in and get a little bit shouty, although I like to remind them that some of their math exists because of physicists.
Yeah. Mary Bradley says, I got here in the time for the ending and the questions. If y'all didn't bring up Rosalind Franklin, another person who was for the double helix discovery.
Oh,
she was, absolutely was. That's one of the most egregious cases of a person who was left off the research, left off the Nobel Prize, who did a ton of really good work. So there's lots of great books about this.
Mm-hmm.
Michael Jobin says, this show has a large Becquerel count. We could have made it one more if we'd covered that topic this week, but all right. Guido Bieber says, now I wonder what happened if the experiment was performed under weightless conditions. I think that's interesting. I mean, you wouldn't have gravity.
You couldn't do this experiment without weight. That's the thing. Is it required in order to get at the radius of those oil drops? It required seeing them hit terminal velocity and knowing that the terminal velocity came strictly from the force of gravity.
Okay, so those are all the questions that I got on the Q&A app. Feel free to throw any more questions in. You heard we just talked about we just talked about interstellar spacecraft. So anything, we love it. Okay, so I'm going to take some questions that have been sent to us by email. This comes from Mudassir Hussain. And so if we launch any orbital satellite into space or to Mars, how do we keep communication with the satellite as our Earth is constantly rotating and we lose our direct link with the satellite? How do we do that?
It's a combination of three different means. One, some of the spacecraft are trained only send messages when the Jet Propulsion Lab, the particular university, whatever thing on Earth is listening, is pointed at the spacecraft. So that's just time-delayed signals. In some cases, it's possible to plug into the satellite system that orbits the Earth that NASA has in place to allow constant monitoring. It's put there to allow constant monitoring with the International Space Station, but it can be used with other things. I don't know if it's currently being used with other things. And then the other thing is we occasionally like other nations, and we use their telescopes, and so we'll listen to things using radio dishes that are scattered all around the world. It all depends on the purpose of the mission, what's going on, and what the energy requirements are. If you have a spacecraft with a very, very weak signal, you're limited on what telescopes you can use, radio dishes you can use to listen. It all depends on the needs of the mission. It's all programmed to work, and we're good at this.
Yeah, I mean there's a worldwide network of radio telescopes as well as satellites capable of communicating to and from. And so at any point there is a radio dish pointed directly towards or in the view of the spacecraft that want to do the communicate, or sometimes they just change the time. They only communicate when the dish is pointing at the spacecraft, and then they wait until the Earth turns again, and then they do more communication, and then they wait. So it's exactly how you think they would solve the problem, right?
It's not hard, actually. It just requires a lot of spreadsheets.
Yeah. Okay, so Greg Perkin asks, so what if the moon was any different? So he says, looking up at our one-faced moon for 33 years now, I've always wished to explain just how different our experience on Earth would be gravitationally if the moon were also rotating to any degree as opposed to being totally locked against the rotation position of the Earth in space. So if the moon was rotating from our perspective, would that cause anything different?
No, if the only thing that changed was its rotation rate, if it was the same mass, same orbit, there would be no human noticeable differences. And I don't think at the distance of the surface of the Earth there'd be actually any noticeable differences.
Right. Wouldn't the only difference be that the rotation of the moon would be slowing down and into a tidally locked position?
Yes, and the problem is the moon has a very off-center center of mass, and this difference causes a torque every time it tries to rotate to not be precisely pointed at Earth the way it is, and this torque slows it down.
But right now, the moon is shifting away from us a little bit.
And that's because the Earth is tidally locking to the moon.
Right. So would those be happening simultaneously? So would the moon... If the moon was still turning, would it still be drifting away? And is that I guess the two things are happening simultaneously, right? That the moon is both drifting away because that's the tidal lock of the Earth to the moon, and at the same time the moon's rotation is stopping from our perspective or from its perspective because of its tidal lock to the Earth. Okay.
Right.
Cool. Noah Ruppenthal asks, will you be playing the new Card Against Humanity science deck in the next Hangout-a-thon?
Why, yes,
Did
we
you
will.
know there was a science deck?
Wait, is this a different deck than the one that has been created by random humans that Nicole Gallucci put together?
I don't know. Okay,
can someone clarify that? I want to know these things.
Clarify, Noel. Clarify. All right. Let me move on to another question. Okay, so Jamal Haq asks, please help me understand how many miles above the Earth does one have to travel in order to break through the gravitation upon the Earth?
You actually don't ever really escape because gravity is something that acts at all distances. It's evil that way.
Yeah, you are affected through gravity from every single particle in the observable universe.
Now, in terms of if we transported you there with the Enterprise transporter, would you fall to your death on the surface of the Earth?
And how?
We'd have to put you probably out beyond the moon before it started to be that you wouldn't get sucked in if you had zero velocity at the moment of being transported there.
Wouldn't you have to go above geostationary orbit? But no, if you're just dropped with no velocity, I mean that's what geostationary orbit is, right? Is you being direct. No, you actually still are orbiting. You just have no ground velocity. So any distance, if you were dropped in Andromeda,
but then you have to worry about what's the dominant thing that's going to suck on you. Are you going to get pulled into the sun? Or are you going to get pulled into something else?
Right.
And it's somewhere out beyond the moon where you're going to stop if you magically materialize right there, you will get pulled into the Earth fast enough that as the Earth zips by at its massive velocity,
Right.
that's the dominant gravity.
Would it maybe be the Lagrangian point between the sun and the...
It's more complicated than that.
Yeah.
I'd have to run models.
Yeah, yeah. If you were teleported in various places and had no... Because the problem is you're always going to have velocity. You're going to have the Earth's velocity around the sun. You're going to have the sun's velocity moving through the Milky Way. You're going to have the Milky Way's velocity moving through the local group. So you have to decide what velocity do you have. And then you're going to get picked up by whatever gravitational force is going to be able to counter your velocity.
And I'm thinking in this wordplay of zero velocity relative to the sun.
Yeah, but the point is that and we've done a whole episode on the Guide to Space, my YouTube channel. Go to youtube.com/Fraser Cain, or Universe Today. I forget which one it is. Anyway, we talk about this, like, are astronauts falling, or are they really falling? Which is that astronauts are not floating; they are falling. They're just not hitting the ground. So definitely listen to that. Okay,
cool. Noel updated us. Phil Plait collaborated with Card Against Humanity to make a science deck. That is awesome. We tried writing to them, and they never responded to our letters. So
well, Phil Plait, come on.
Yeah, I know. He's kind of he's more famous.
All right. So Shubdawan asks, is it possible that dust on Earth is from a nebula, or how does dust come to Earth? Same with water. So did the dust on Earth come from the nebula?
Well, okay, it depends on what dust you're talking about. The majority of the dust in my house comes from
you and the dogs.
It comes from, actually, in our house, because our house was built more than 200 years ago, 230 years ago. It comes from the plaster on the ceiling. So most dust on the planet Earth comes from structures on our planet not being as rigorously held together as one might wish, and just periodically losing track of some of their molecules. Human beings lose track of their skin. We sort of leave cells everywhere we go. The dirt gets kicked up by the wind. Rocks slough off layers from the wind and fluvial water processes. All of these things create dust. Now, the stuff that made up the Earth originally in the solar nebula, yes, that came from out beyond our solar system by definition, and was used to form our solar system. It was part of other nebula, parts of the star-forming region we were originally part of. But dust, as you encounter it in your house, that's probably your own skin cells, your housemate's skin cells, bits of your ceiling, all of that sort of stuff you probably don't want to think too hard about.
Right. And we actually did a whole episode on where does the Earth's water come from. So
yes.
If you want that answer, check that out. Okay, I got one more here. So the Earth's spinning speed. So the Earth is spinning about 1,000 miles per hour at the equator, and the Earth is slowing down. So it slows down about 1,000th of a second every day. I don't know if that's true. The Earth is spinning and slowing down. That means it used to spin faster. So the question is, how fast was the Earth spinning 6,000 years ago? Can you tell me how long days were in this period?
So 6,000 years ago, it wasn't that much different.
Yeah.
I think the earliest records that we have, the Earth was probably, from what I recall, and this isn't my field, I have vague memories of it being closer to a 20-hour day within humanity's existence, and early on being as significantly shorter than that.
So we're at 1.4 milliseconds every 100 years.
Okay.
So that is not fast. So it would have just been like maybe, I'm trying to think, 100 years, 6,000, so 60 times, so 60 milliseconds shorter than it was today. So you wouldn't be able to tell. It's only when you added the millions and the billions of years ago that it made a big difference. So that can't be used to rain on the creationist parade, I guess, is what we're sort of expecting. Okay. Do we have time for one more?
Trying to look up how fast the Earth was spinning after the Moon was formed, and I'm not finding the result.
So Guy Shepard asks, was the Earth formerly a gas giant?
No.
And so this, well, hold on. Just 1 second. So there is some really interesting recent research about how Neptune-sized planets may have been stripped away, had all their additional material stripped away from by, as they used to be hot Jupiters or, whatever, hot Neptunes, and then they had all the material away, and they could have ended up as super Earths. So there's one line of evidence that says that in some cases this could be happening.
Right, but you end up with a completely different density profile than what we have here on Earth.
Yeah.
So you look at a place like Mercury, you can tell there was clear stripping of Mercury just because the core ratio compared to the rest of the world is so great. We don't have an anomalous core ratio, and in fact, while we are slightly above normal, this is because we have a moon that stole all of our lightweight stuff.
Right.
So we can attribute all of the anomalies in our own density profile to the collision that formed the moon and ate a different object.
Right. All right, we better wrap this up. Hey, thanks everyone for watching the show live. Apologize for the switcheroo, and we'll switch it back again next week. Thank you, Pamela. Once again, let's remind people on how they can watch the Hangout-a-thon.
You can go to cosmoquest.org/hangoutathon and find out everything about what we're doing. During the event, we are actually going to switch the homepage of cosmoquest.org to reflect the Hangoutathon and all the ways you can get involved. If you want to be a corporate sponsor, I'm still looking for those, so reach out to me, starstrider@gmail.com.
Perfect. And follow Pamela. You have to talk now, but follow Pamela. Here, I'll switch it.
Starstrider.
Starstrider with a Y, right there. Or follow me, F. Cain. And subscribe to this YouTube channel, the one that you're watching, so that you'll get notifications that we've done new shows. So, and the ones with the questions are so much better than the other ones, and you get to see what we both look like and say you don't look anything like we thought you would sound.
And you also get to hear all of the mistakes that Preston in his awesomeness gets rid of. Gets
rid of, yeah, exactly. All right, well, cool. Well, thanks everyone. Thanks, Pamela. We will see you all next week.